Hey folks, I hope you all had a great holiday. Sorry about the delay in getting back on these videos, but we did have some severe weather conditions where I am. We had to deal with those, and then of course we had the holidays, but we're back now. So we're going to continue on with our close look at the oscilloscope and the function generator. Now, in the last episode, we went carefully through the function generator. We established that it's fairly flat, and it's it's got some issues, but it's usable. And today we're going to use it to look at the oscilloscope and go through it and see how it responds, how well it represents the signals that are coming into it, and go through its controls and figure out how to use it. They don't give you a lot with it as far as instruction is concerned, so basically we're going to have to kind of figure that out ourselves. But in helping us do this, I'm going to be using a power supply, this nice little Hewlett-Packard here. Unfortunately, our kit power supply, this one, has developed some strange issues over the holidays, so I've got to look into that, and that'll be the next video. We're going to have a look at this, take it apart, and maybe find out what the heck is wrong with it. It's producing some awful noise, not audio noise, but electrical noise, and so we'll have a closer look at that in the next video. And also to help us out, we're going to use this Oscilloscope. And we're going to use that to keep an eye on things, just to make sure that the kit scope is not lying to us. Okay, so let me set up for that and then we'll get started. All right, folks, so we got the oscilloscope here, the probe or cable that it came with, the instructions on how to calibrate it, and we got these little feet that we're going to install on it too. And we'll probably take this little bit of cover off the screen, and let's go ahead, get these feet on it. Here we go. Now I find these feet are pretty flat and hard and pretty slippery. So what I'm gonna do, I've got these little silicone dots. I'm gonna stick those onto the bottom of the feet here, just to give the thing a little bit more resistance to sliding around on a hard surface. They should stick right on there. There we go. And that provides much better stability. Nice. So the next thing we're going to do, we're going to go through the instructions here about on probe calibration. So let's see what we have. We need to connect the red clip to the test signal terminal and leave the back clip unconnected. Set the sensitivity 1 switch to 0.1 volts and sensitivity 2 switch to X5. Set coupling switch to AC or DC. Adjust the time base to 2 milliseconds. You should see a waveform similar to that shown in the photo below. If the traces are not stable, adjust trigger level, blah, blah, blah. Turn C4 capacitor with a small screwdriver so that the waveform displayed is a sharp right angle, photo C. And set sensitivity 1 to do 1 volt, sensitivity 2 switch to X1. We'll keep all of the settings unchanged and just C6 so that the sharp rectangle waveform is displayed. Well, okay, well let's do that. Let's set up for that and we'll be right back. Okay, there's the cable connected. We'll connect the red over here like that. Set our sensitivity 1 switch to 0.1 volts. Set the coupling switch, I'm going to set it to AC, and then set the sensitivity 2 switch to X5, And now we'll go and adjust to 2 milliseconds. Where are we now? We're at 1. So we need to adjust to 0.2 milliseconds, which is right there, 200 microseconds. Now we need a tool, got one of those, to turn C4, as C4 is this lower capacitor here, to get a nice rectangular waveform. It looks like we've got some spikes at the beginning of it, so we need to adjust those out. That's looking pretty good. Now if we were going the other way, it would look like this. If you have those rounded edges, we just want to get rid of those. We just want it nice and sharp rectangular form without any spikes or rounded edges. Okay, that looks good. Now we set the sensitivity switch to 1 volt and set the sensitivity 2 to X1. Keep all other settings unchanged and adjust C6 so that a sharp rectangle waveform is displayed. We got a little bit of rounding on this one, so let's see if we can improve upon that. There we go. That's looking pretty good. Okay, so I guess we're all calibrated. Now what I'm going to do, the next step, is we're going to hook it back up to the oscillator, and then we're going to run it through a specific set of frequencies on a logarithmic scale, and we're going to get the frequency response of it. I'm going to hammer that frequency response, all the results that we get back out, into an Excel spreadsheet so we can get a graph of the frequency response of the oscilloscope. And we'll briefly also go through all the different controls and stuff like that here. I'll read up about them, and then we'll come back and we'll start off with first going through the controls, and then we'll do the frequency response. Let me set up for that. Okay, so let's go through the controls of the oscilloscope a little bit here. So right here over on the side here we have the coupling. We have ground, which will just give us a flat line. We have AC, which will take out any DC bias that's coming in through the connector, through the cable. And then we have DC, which will include both the AC and the DC bias. So you can see right now, being connected up to the oscillator, that we do have a DC bias. So putting in the DC puts it off the screen. So we'll keep it through most of this here. We'll keep it through the on the AC settings through what we're doing here. Then we have sensitivity. We have 1 volt per division, 0.1 volts per division, and 10 millivolts per division. And here we have a sensitivity in times 1. So if you have on times 1 and at 1 volt per division, we should actually be seeing 1 volt peak to peak here, because that's what I'm supplying with right now. And then times 2, it should go up a little bit lower, half a volt. So we'll go down to more sensitivity here. So right now we're at 0.1 volts per division, but we've got a times 2 setting on it. So we should be seeing approximately 0.2 volts per division. And if we go to 0.5, then we'll see half a volt per division. Now, over on this side here, we have a confirmation button. We have a plus button, a minus button, and a select button. The select will change what particular parameters you can adjust with these buttons here. So if we go around here, right now we're on time base. If we press it again, we'll go up here to trigger level. Pressing it again, we'll go to the kind of trigger, whether it's auto, normal, single, shot mode. So we have those 3 different choices there. Next, we go over to whether it's triggering on a rising edge or a falling edge. And the next, we're looking for this here controls actually the built-in oscillator. So it's set for a duty cycle of 50 hertz or 50%. And over here we can set the frequency of the built-in oscillator. Right now it's set to 1 kilohertz, and we use that to do the calibration, the last step. The next one here, we can set the position of the trace, so we can set up or down on the screen as we desire. So we have here choices of how it's displayed. So here with X10, we've got 2 volts per division. X1, we've got 200 millivolts per division. and they're the two choices. And this here would be for setting it up for a probe like this kind of probe that has a times 1 and times 10, so you can get a reading here that is adjusted to the probe itself depending on the setting. Now most of the times you would use a probe like this in times 10. That's where these things are calibrated to work. Times 1 is not often used very much at all unless you've got a very large signal and you're just trying to get an idea of the waveform, but the frequency bandwidth goes way down in times 1 because these things really are designed to be used as high impedance times 10 probes. And then we come back again and we're at our time base. So this here's an indication, should be of whether we're on DC, AC, or ground. This here should be telling us whether or not we're 100 millivolts of division, 200 millivolts of division, 500 millivolts for division. And this here should be telling us whether our base is at 2 volts, 200 millivolts, or 20 millivolts. Okay, now we seem to be in stop mode, so click that to run. So this is your run stop over here. And also if you press it down for a few seconds, it looks like about 3 seconds, it comes up with all the measurements. So this allows the scope to display its internal measurements of what's going on. We'll turn that on and off depending on what we want to see. But that's it. So if you want to get rid of that, press this down for another couple of seconds and it goes away. You can see the entire waveform. All right, so let me now set up, I got to set up my computer here to take my measurements and record them, and we'll come right back to that. Okay, so we're all set up now to take some frequency response measurements of the little oscilloscope here. So we're going to be taking 5 measurements per decade over just 5 decades from 10 hertz to 251 kilohertz. And we're going to go in logarithmic steps. What that means is we're going to start off with 10 to the 1, which is 10 hertz, 10 to the 1.2, which is 15.8 hertz, 10 to the 1.4, which is 25.1, and then we go along, see this sequence, we get up into 10 to the 5, which is 100 kilohertz, 10 to the 5.2 is 158 kilohertz, and 10 to the 5.4, which is 251 kilohertz, for a total of 23 measurements. And we'll punch those into the computer. We're going to produce then a graph. We'll probably produce 2 graphs, one with a dB output and the other with a linear output, just so we could see the difference and point out why you prefer one over the other, depending on how the frequency response of this thing turns out. And as I said before, we're going to be using the little kit oscillator function generator to produce the signals, and we already saw that that is pretty flat. And I'm going to be using my Siglent 600 megahertz Siglent scope to keep track of things, just to make sure that nothing strange happens with the oscillator and that we get a nice flat response or flat output from it, so that anything we do record on this will then just be the result of the frequency response of the scope itself. As I go along through this, I'm going to have to make adjustments to the time base. I'm going to have to record the values based on the automatic reading of the measurements here, as we see there. So we're starting out, as you can see, at a 1 volt input. That's what we're showing on the Siglent scope as well. So we've got 1 volt coming out of the function generator, and we're seeing 1 volt coming out of this, more or less. I mean, it's close enough. So we're going to take the measurements starting with this one, and we'll go up from here. So the next measurement will of course be at 15.8 hertz, then 25.1. Now I'm not going to drag you through all of that, so we'll speed up the video from this point on, and I'll record the values as I go along, and we'll see at the end, and I'll show you the results. All right, let's get started. So that's the end of the measurements. We took it out one more step to 398 kilohertz. Let me punch all this into the computer now, and we're going to come back with the graphs. All right, here we are back with the results of the frequency response. So we can see, yeah, it's pretty flat. I mean, it's a little bit rocky at the beginning, but then flattens out from about 200 hertz all the way up to up into the higher end of the audio range anyway, up into about 20 kilohertz, and then begins to taper off rapidly. Now, the specifications do say that it is good for 200 kilohertz, which seems to be true, because we're at minus 3 dB at this point, which is just past 200 kilohertz. So it does meet the specification that's listed for it, and it's pretty flat. I mean, it's not bad. Here's the same frequency response, but in a linear vertical scale. Now you can see what happens here is the logarithmic vertical scale tends to accentuate things a little bit more, so you see more of the detail, especially going negative. Yeah, so this is actually not that bad. I mean, you could use it for measurements all the way from about 100 hertz all the way up to 20 kilohertz with no trouble at all. Even the lower frequency is not too bad. The half dB does not represent a heck of a lot of deviation. As you can see here in the linear scale, it's about percentage, less than 5% of the total value. So yeah, it's not a bad little scope. I mean, for the money, it does deliver what it says it delivers. So yeah, that's pretty good. I'm happy with that. So the next video that we do will be concerning the power supply. We're going to try and have a look at it. We'll tear it apart and have a look inside it. We'll put it through some paces like we did with this, and we'll make a determination on this as well. But I think so far the meter has turned out pretty good. The function generator has turned out pretty good. And now we can see the scope has turned out pretty good. Well, thanks for watching, and we'll see you in the next one. Bye-bye.